Welcome to the Second Annual Enigma Forum. Very happy that you could be here and happy that we are here. We hope to present some very interesting information this afternoon. We have 4 speakers. Actually, Paul Reuvers didn't get a chance to speak last time. He's going to be our first speaker. And Jerry McCarthy and Franz Pichler and Klaus has brought his extraordinary Enigma replica, and he is going to demonstrate it and show it to us. We invite you over to our tables in the flea market. As always, we try to have a gathering of crypto enthusiasts and crypto collectors. And you will see some Enigma machines, and it's a constantly changing amount of equipment on these tables because we are always trading. And so when you see one piece of equipment for an hour, it may disappear and another piece of equipment may take its place. We are always trading, and I think you will find it interesting not just to stop off once, but to come several times during your trips through the flea market. I apologize that I cannot present in German. If I tried, I think it would end up being a comedy rather than a serious lecture, so please accept my forgiveness. Some of the speakers can speak German, and we will take a vote to see whether you would prefer the speech to the talk to be in German or in English. I invite you again to our tables. This is Klaus showing off his Enigma replica last year, and another extraordinary piece of equipment that showed up last year. At the table, you will see a number of crypto historians, people who specialize in the history of cryptological equipment. This is a gathering that we had at Bletchley Park in 2009, and the arrows up here point to the people who are present today and will be out in the flea market to answer your questions, to talk to you about crypto equipment and crypto history. We have an extraordinary timeline and map of the evolution of the Enigma that has been put together by Paul Reuvers and Marc and Frode Weiraud. And Paul and Marc are here, so if you have questions about this timeline, they will be happy to answer. It is an evolving timeline because we are always discovering new things about the Enigma, and Paul keeps updating his timeline to keep up with those discoveries. But it is extraordinary. Trace all the different known versions of the Enigma and how they started out and how they ended up in the final production stages. We have a listing of the major historians and their websites that you can see at our tables. And we also have an Enigma book and an Enigma CD if you want to go into the subject in more depth. The first speaker is Paul Reuvers and Marc Simons, and they are going to talk about the Russian Fialka. The Russian Fialka is an extraordinarily interesting piece of equipment, very, very, very complex and very interesting. You will see at least one Russian Fialka for sale in the flea market. It has 10 rotors. They rotate in different directions, and Paul and Marc will tell you much more about it. But I refer you especially to their wonderful website. Their website has really become the central focus of information in the area of crypto history and the various machines. Every time I find something, I talk to them and they, oh yes, it's on our website. So I highly suggest that you go to their website. Very, very easy to navigate. You look at the left side of the website, you just go down to what you would like to learn about, and there it is. It's just an amazing and wonderful resource for us. The picture of them at the Bletchley Park reunion, Paul is on the right, Marc is on the left, and one of the extraordinary machines that they found and are displaying at the Bletchley Park reunion. The Fialka is a very, very exciting and interesting machine, both outside and inside, and I look forward to hearing their discussion and description of it. One of the things that you may not know about the Fialka is that Paul and Marc have put together the only real complete, detailed technical manual in English for the Fialka. They have actually reverse engineered the extremely complex circuitry of the Fialka, and the diagrams in the book are extraordinary, easy to understand, but very, very complex. And the book is something that they will also be selling at our table. So if you are interested in going into the Fialka in more depth, I certainly recommend that you take a look at their book and considering adding it to your collection. And with that, let me introduce Paul and Marc, who are going to take over.
Well, thank you, Tom, for the introduction. Before I start, I would like to ask the audience whether to do this in English or in German. How many of you do not speak German at all? Okay, that's quite a few. How many speak only German? Right. Well, in that case, I suggest we continue the presentation in English. There's plenty of pictures and images, so I think it should be okay. If there's any questions, please save them until after the presentation, unless you think that we are making a gross mistake, then please interrupt. Today we're going to talk about the machine that's displayed here behind me, Fialka, which is a relative of the famous Enigma machine that was used in Germany during World War II. The German machine had only 3, or in some cases 4 rotors, and we will see today that Fialka had many more rotors. Was that the only machine they used during the war? No. During World War II, we already had an M-100 machine that we've never seen before. And there was a machine called K37, which was a copy of a Hegelian machine. So the development of Fialka started just after World War II, just around 1955-56. The machine was used in the entire Warsaw Pact countries, so in Russia itself, Poland, Czechoslovakia, Hungary, and many more other countries that we even haven't heard of it. After the Cold War, most machines were taken back and have subsequently been destroyed. So today we will show you the machines that have miraculously survived it. The name M-125 is the official name of the machine, and the code name was Fialka, which is the Russian word for the English word violet, the little flower, of Deutsch Falschen. Right. Here's an image of Falschen. Yeah. We first got in contact with this machine back in 2003, when we got an opportunity to see this machine live in action. And the machine that we got was in very, very bad condition. It had a damaged reflector and a damaged entry wheel. And this is how it came out of the machine. It couldn't work, it couldn't be operated. It was glued together and all the contacts were fixed. So after many weeks of restoration, it looked like this. And it started to work again. And that was a unique moment. So we will now take you through this little history lesson. We found out in the first weeks that there were 2 models basically. The one that you see here is the initial Fialka model, which can be recognized from its round keys. The keys have 2 letters each. One is Russian, one is a Latin letter. There is another model, which is introduced slightly later, about 10 years later. There's a more advanced model, which you see here, and it has square keys. It has the same Russian and Latin text on the keys, but also adds country-specific letters to it. So for Hungary there was another machine, then for Czechoslovakia, and for Poland, etc. But there is something else to show you, which I think most people have not seen before, and that's a Russian Fialka machine that has only recently popped up. And it is the later model with the square keys, but in this case it only has rounded keys, because Russian doesn't need the Latin characters. But this one has Russian text, Russian punctuation marks and numbers on it, and has rounded keys, but is still the newer model. And it has been discovered in Lithuania. It was given to a KGB sniper on his retirement. So he got that. Unfortunately, there were no wheels in the machine, so we still have no idea what the Russian wheels look like. Today, however, we will concentrate on the basic two machines. And that's these two. So with the rounded keys, which we normally call the old model, and with the square keys, which we call the newer model.
So we are going to look at the outside of the machine. When you look at the top side, then you see here, of course, the keyboard, and there is the printer. There's a printer head around here. There is an output, being able to output the signals to a teleprinter. And there is a tape puncher under here, and a punch tape reader under here as well. So when you open up the lid, then you see the rotor set, of course, and you see the mechanics. It's yeah, very compact. From the side view, one thing is very interesting. It has a switch here, and the switch is done there for 30 or 10 characters, but the 10 characters are actually only numbers. But the Russians love to use numbers for messages. So with this switch, you can switch off actually letters and use the numbers only. I'll explain later how they use that. There is a card reader at the side here, being able to put in a punched card for each day. They used a punch card, and they actually used a configurable wheel. So they actually used a complete free matrix of holes and contacts, so that they put it in a card here, and that acts as a configurable wheel. Very interesting. And a 24-volt input. So the right view side, we see the 5 letter groups switch here. It's only giving a pulse with 5 letters. You have a pulse, and it's very easy to read. That's the only thing it does. And there is the output again here, output connector.
So that's how we started. So we discovered that the machine has certain things in common with Enigma. It is a machine with wheels. It has a keyboard, but instead of the LAN panel of the Enigma, it has a printer. It prints directly onto paper. It has an entry wheel, just like Enigma, and it has a reflector, just like Enigma. And most people who are into Enigma know what that means. It means that the letter can never be encrypted into itself. So if you press the letter A, it can become any letter, but never an A. That is because of the reflector. We will see how the Russians solve that. But we see also some differences. Instead of 3 or 4 wheels, they had 10 wheels. Like I said, paper instead of the lamps. 30 contacts in each wheel, the 30 letters of the Russian alphabet, the 30 most frequently used letters. And it had, in some cases, a configurable wheel wiring. So you could take the wiring out of a wheel, which we saw later, and change it. Now, in order to understand the machine, we will show you parts of the circuit diagram, but to make it more understandable, we go back to the Enigma circuit diagram first, and I assume that most people know how the Enigma works.
Okay, so the schematics of the Enigma is reduced to 4 letters only at this moment. So when I press the Q, the rotor rotates first, 1 step. Then a new circuit is coming along, because in the rotor there is wiring, and each wiring is unique for each rotor. So rotor 1 has a specific wire, rotor 2 has a specific wiring, and 3 as well. So the current goes from the battery through the switch to the Eingangswalze, and then going through the rotor wiring. The Umkehrwalze reflector reflects back, goes through the rotors again, and then here we have the current going, and there the W is going. So with this specific rotor setting, when I'm at the other side, I'm communicating with my friend, and he has the same rotor setting at this moment, and he presses the W, then there is no other chance than that the Q will light up. So that the current will go exactly the other way around, with the same rotor position. So this is actually basically the Enigma schematic. So when we look at the Fialka, we can actually see that it's quite the same, except that there is some more wiring, but the basics is exactly the same. It is a reflector machine as well. So you have the keyboard, the 26 contacts are going from the motherboard to the Eindhoven enter disk through the rotors, Hoekewaldse function, back, and then keyboard and then lambda. So it's actually the same. When we show this diagram, it looks a bit different, but it's actually the same again, because we have the keyboard here, but now they added this programmable matrix I was talking about. It is the card reader. You have the rotors here, and you have the reflector here. So the current is going like this, going back here, and then you have your result. In this way, they put kind of a diametrics here, and they generate actually a 5-bit code for a teleprompter, but it could be 30 light bulbs as well. I mean, it's exactly the same thing. So, but there is a problem here, because they have this reflector. And they have invented a very nice feature. A letter can be itself. How did they do that? Because with the reflector you normally can't do that. Because a letter can be anything, but they invented something very nice. I've got the schematic from the reflector over here. So they got out one wire, and they said from this time on the letter can be itself. Because when the letter is coming from that wire, the A is coming out as an A on this line here. But if I disconnect one wire, I have one left over. I can't leave it. I have to do something with it. So they added something to it, and it's we call it the magic circuit. Now, what does that do? If you look at the side of the Enigma, the Fialka, then you see the electrons of the magic circuit around here. There are 3 transistors and some diodes, and this is actually the schematic here. And what it does is the following. When I encode a message, then if the contact 16 comes out, it runs to 18, and then it runs to 24. But if I'm decoding it, I'm switching it over to let it rotate the other way around. So 24 goes to 18, goes to 16. So I actually have 3 wires out of my reflector, and I add this funny circuitry around it, and it acts like a rotating thing. It's very interesting. So the magic circuit. And for encoding and the decoding a message, I only have to swap 2 wires of this magic circuit, and that's done here. So if you look at the switching circuitry, it is a very complex baker-like thing with contacts and feathers and stuff, and so it's just amazing when you get it from each other. You ask yourself, can I get it assembled again? It's just horrible. So we are looking at the key. We are looking at the main schematics again here, and the keyboard here, and you see the magic circuit around here. So it can be that the signal goes like the letter can be itself, right? But it can also be that the magic circuit is reflecting it back again. See?
Right, quickly look at the keyboard. We see the 30 characters of the Russian alphabet, 30 most frequent letters, and they've left out a couple. For example, the letter J can be replaced by an I without influencing readability too much. Good, now look at the rotor set for a moment. The rotor set is parallel to Enigma, except we have 10 rotors, but like Tom explained in his introduction, the rotors are rotating in different directions. The even rotors move backwards, and the odd rotors move forward. I'm looking from the top. Here you see a set of rotors, 10 rotors on a spindle, comparable to Enigma. You can take the rotors off or put them in a different order. And there's two different types of rotors, two different types of wheels. So these are the initial wheels that were supplied with the early machine. They have a fixed wiring. So each wheel number A has the same wiring as another A, of course. You can see it from the front, from the back, and from the side here. And the later introduced wheels, I think they were introduced in 1972, if I'm correct, had a replaceable wiring. You could open those wheels and you could take out the wiring and put it back into 30 different positions. But you could also reflect it, so put it in back forward so that it get mirrored, and then in 30 different positions. And you could even put the wiring of one wheel into another wheel. So a wheel has certain notches where it takes over the next wheel, and if you put the wiring of that wheel into another wheel, it gets even more complicated. Now, to make it even more complicated, the wiring was different for each country of the Warsaw Pact. So Poland had its own wiring, which was different from Czechoslovakia, different from Hungary, different from Russia. So they were allowed to use the machine, but they were not allowed to communicate together. Only in case of war, and in case of war, they would spread around the 0K wheels, which were identical for all countries. Now, if war broke out before those wheels could be distributed, they had a set of wheels in a wooden box, where each country had the wheels of the neighboring country, just for emergency cases. But as we all know, it's never been needed. But here you see again how the wheels move. What is very, very complicated is that this wheel always moves forward, wheel number 9, and it influences the movement of the wheel 2 positions to the left, wheel number 7. And that influences the movement of 5, etc. And for the odd wheels, it's just the other way around. Wheel 2 always makes a step on each key press, and that influences wheel 4, 8, etc. Now, how does that transport mechanism works? If we look at the machine with the wheels in place, and we take out the wheels, you see a complex construction of fingers, as we call them, even and odd fingers, in the shape of 2 cones that move, make a circular movement. So these fingers move and these move. And it comes from underneath the wheel and it grabs the wheel from the other side, and that's how it moves. If you want to see that, come to our stand tomorrow and we'll show you. Here you see that there's a notch on the wheel that can push away one of these fingers so that the next wheel cannot make a step. So very, very, very complex. Here you see it once more again from the front. And now let's move over to the card reader. The card reader, as Marc explained, is a very nice little piece that basically replaces the stacker board of the Enigma. But it's more complex. It gives more permutations because any combination can be made, which is not possible on the Enigma stacker board. On the Enigma, letters are always swapped in pairs. If an A becomes a B, then a B becomes an A. And here you can make any combination you like. The card reader is on the left side of the machine. You can pull out a little drawer where you can put in a punched card. In this particular case, on this photograph, you'll see a metal triangle, which is used if the card is not in place. And that card simulates the unity matrix. So A becomes A, B becomes B, etc. As if the card reader was not there. Here you see an example of a punch card, and this is the only real punch card that we've ever seen. So the machines are always found without the card in place, because the card had to be destroyed at the end of the day. Just in case the enemy would find a machine, they would never find a card. But Tom was so lucky to find a card in a machine one day. Here you see the circuit diagram of the card reader, nothing special. It's a set of 30 contacts, and if you close the drawer, the little holes in the card carry on some contacts when you close the drawer. So if you look at the metal triangle here, it does exactly the same as a card with a diagonal row of holes. It's identical.
The keyboard of the Fialka is actually nothing really special, except for the mechanics. It's beautifully made mechanically. It is a mechanic and an electrical combination of a row of contacts together with a 5-bit encoder.
Can you speak a little bit louder?
Yes, I can.
Thank you.
So it is a combination of a row of contacts with a 5-bit encoder at the left-hand side. And you see it in the next picture here. This is your encoder sitting around here somewhere. And the 30 contacts are sitting around here. And if the letter is itself, then this signal I showed you last time just tells that the encoded letter here is the result actually. So the letter can be itself, right? So the 5-bit encoder then is converting the results from the rotors and the counter back to here. It's nothing else than a diamatrix creating a 5-bit encoded character from these 30 contacts. And then you can punch shape the whole thing with a puncher. The puncher itself is in the machine as well, as I told you lately, and then you see here. You see the mechanics of the puncher here. It's somewhere here. So the tape is going through here. This is the transporter going through here. And this one is the hammer, hammering the letter or punching the character in. And a switch enables if you want to print or punch or do both. It's very nice. The printing head, by the way, is like this shape, and from the different countries you have different print heads, so different character sets around.
Okay, now I'm going to show you a little feature, and that's the 3010 switch. Marc has already announced it in his, let's start, there's a little switch underneath the card reader that allows you to switch between 30 letters or 10 numbers. Like Marc said, the Russians love to do things in numbers. For example, the weather forecast was always in numbers. But how do you do that? How do you reduce a machine with 30 contacts into a machine with 10 contacts only? We have this complex construction with a magic circuit, and we have 30 wires coming through each rotor. So what they did is they constructed a reduction circuit so that 20 wires were taken out of the reflector and were fed back into the input. And they loop around until they come out on the encoder again. And that reduction switch is a very complex construction that's underneath the machine. Sitting at the very bottom of the machine is a slide switch with 2 positions. You can see them here. The white lines indicate the positions. This is position 1, that is position 2. And after many weeks of tracing wires, we came to the conclusion that this is the way it works. And that's only part of the machine. To cut a long story short, we spent about 3 months spare time researching this machine, and we came to this circuit diagram. And a year later, we had this printed in A0 size on a stand. And there was a guy coming up, a former Fialka repairman from the DDR. And he said, "Where did you get the circuit diagram?" I said, "Well, we made it." He said, No. Where did you get it?" I said, "Well, we made it." He said, "But it was exactly like that. Only not in color." Okay, I see that we have passed our time already. Can I take 2 more minutes, Tom? Is that okay? Yeah. I'll quickly show you the way the keys work, the daily keys. They had a little wallet in which the cards were stored. And the daily key consisted of a printed card with the settings of the rotors, the ring setting and everything on there, and a punch card, of course, that was changed every day. And now a very short example of how the Fialka was used. It was used in many situations by the police and by the military. But this is a very well-known radio van, a GAZ-66 truck from Russia. with an R142 radio set in it, and you see the set. And this radio set has space for 3 secret devices. I'm a bit too fast here. One secret device is the Dutching, a boost encoder that you've seen on the stand, Thomas one on the table. Here is a spot for the Fialka machine, and there in the corner is a spot for a voice encryption device called Jato. Fialka has an empty drawer here under the radios, and a lot of people have tried to put a Fialka in there and would never fit until we figured out that the Fialka had to be rotated by 90 degrees. So the keyboard is not like this, but it's like that. And then it fits perfectly well. Here you see the track from the top, and you see that the radio set is here, and Fialka is right there. Fialka was never put in this track because it was only to be distributed in case of war. So none of the operators of this radio set will confirm that Fialka was in fact used in this track, but it was. And now, very quickly, the accessories of the Fialka.
First we have the regular power supply, and then we have the special power supply, and they kind of did a tempest circuit in it. So the current draw from the Fialka was equalized for each character. Very interesting to learn how this has been done. Then some extra print heads, a test reflector, an oil can, how do you call that? Crank to be able to correct your position, and a canister with extra rotors in, and high quality Russian tool set, and then with the complete setup look like this. So when you compare that with this, what we have at the same time, this is a typewriter from the same age. We use that. And look at the size of Fialka, it's amazing. And it does encryption and decryption as well.
Whereas the one on the left is just a teleprinter, the CST100. Okay, so let's resume for a moment. This was the machine used by the Russians during World War II, K-37, an exact copy of the Hagelin B211, but adapted for the Russian alphabet. This is a post-war machine, M-130, used for the weather forecast in the Warsaw Pact countries, very complex encryption. And they had this machine, M-105, or codenamed AGAT, which was an unbreakable machine using the famous one-time pad Cipher. So even the Russians had that. This is the end of our presentation. So I hope you enjoyed it. If you want to know more, if you want to know more, come visit us in Hall A or visit the website, as Tom already explained. Yeah, thank you. Yes, are there any questions so far? Yes, please.
Was the Fialka ever broken? And if so, by who?
Yes, it's a very good question. We had informal discussions with people who worked for the Austrian Secret Service, and they told us that it was broken with the help of American computers. But we needed to find someone to confirm that statement. So we did a lecture in England at Bletchley Park, where somebody asked the same question, and we said, no, it was never broken. And there were two people in the audience who said, well, this can't be true. So they were from the British Secret Service, and they came up to us afterwards and said, it was broken. So, it was broken with help of a Cray 1 computer in the 70s by the NSA. The NSA gave the computer on loan to the Austrians. And since Austria is not a member of NATO, but still good friends with America, they could share the information with America, not with NATO. And the Americans could decide which information they wanted to share with NATO and which they didn't. So that's how it worked for a long time. Right. Any more questions? Okay.
Thank you, Paul and Mark. That's great. Just switch over the computers for a moment. Our next speaker is Jerry McCarthy, and He is a software writer, and what else? Why don't you tell people what you do, Jerry? It would be great. Thank you. Jerry gave a wonderful talk at the Crypto Symposium in North Carolina a few months ago, and he's going to talk to us about his work with the SD40 and 42.
Okay, leider meine deutsche Kenntnisse ist nicht so gut, deshalb werde ich diesen Vortrag in Englisch stellen. I'm going to talk today about something different than Enigma, just like Fialka is different than Enigma. But first of all, I'm going to quickly reprise Enigma, just so I can explain the differences. This picture you probably know, everybody, by now. There are three rotors and a reflector, and each time you type something on the keyboard, the rotors move, and you get a different letter out as part of the translation. I typed in 4 A's and I got BDZG, BDZG out. That's an Enigma at work. The Enigma is decrypted by using the box top right, which is a bomb. There are various versions of this bomb. The Americans have a much grander one with 4 rotors, but 3-rotor bomb for a 3-rotor Enigma. I'm going to be talking about this machine and this machine, which is used for decrypting the machine on the left, which is called a Colossus. So the basic encryption machine, Verschlüsselungsanlagen 42, SZ42, which I will say for ease of saying it. It uses 5-track tape. For those of you who don't know 5-track tape, if you think about 5-track tape, there's only 31 characters you can have on 5-track tape, and that means you therefore have to double up the use of the tape by having letter shifts and figure shifts. So on the letter shift you have the letters and some room for some control characters, and on the figure shifts you have punctuation and the numbers. The encryption is a process of changing each of the bits of a character using a key stream. Using the exclusive OR algorithm, where a whole, exclusive OR with not a whole, gives you a whole, and that's the same thing in reverse. But if you have 2 things which are the same, that is 2 blank pieces on the tape, or 2 holes on the tape, then you get a blank. So the encryption process for a message. I have here a message which is kind of trivial. Line shift, letter shift, message, character return twice, line feed twice. And the fact that I've duplicated those control characters is part of the story. I'm encrypting against the key string, which is just the letters A through M. And I end up with a crypto text string, which is MIL, character return, space, and so on. This is reversible. If I apply exactly the same algorithm to the crypto text, using exactly the same key, of course, I end up with the original message. The machine that was encrypting this, the SZ42, has an input of 5 channels, which is the 5 holes on the tape. 5 wheels, with a different number of positions on each wheel, and the number on all the positions of the wheels are all neutrally prime. In fact, they are all prime except for one of them, which is the 51. So you have 2 encryption sequences. The 5-track data comes in here. Each bit is changed or not changed depending on the value of the key character to a new 5-track stream, and then a second 5-track stream comes out of the output. This set of rotors rotates with every character. This set of characters rotates somewhat randomly, it's pseudo-randomly, under the control of 2 drive wheels. Here you can see the 12 wheels which I was pointing out. 5 of these are data wheels. There's two motor wheels in the middle, and 5 more data wheels. Whether or not a wheel is considered to have a hole or not a hole is dependent on a little switch, and I hope you might be able to see here, there's little tags here, some of which are in the central position and some of which are offset, and they count basically as the data stream for the encryption. There's a well-known story that a message was sent twice using the same key, using the same start position, but the message was sent slightly differently. So the message was first sent with the full text Spruchnummer and various other full texts. It was abbreviated on the second transmission, but the same key position was used. So Spruchnummer was converted to, for example, the letters A through L. And Sprucken are on the following characters, A through G, and then a different character at this point because the U in Nummer was replaced by an R in the abbreviated word Nummer. Now the H here is the exclusive OR of the U here and the key. The M in the lower line here is the exclusive OR of the R from this abbreviated version of Nummer and the same key. This means if you exclusive OR all the characters of interest, so the M and the H and the R and the U, you're basically stripping out the key and you're just ending up with 2 plaintext characters, the U and the R from the original plaintext. And to do this automatically, to detect what is going on after that, this machine was designed. This machine is, this picture is from the 40s. It's almost certainly posed because there's nothing happening, and I don't think Colossus was ever allowed not to be running. But as you can see, that there's the Wren's operator is changing a tape here, and the tape that is not being changed is also stationary. The National Museum of Computing, which is on the Bletchley Park campus, has rebuilt Colossus, and this is a rebuild. And it is available for anybody to go visit. And the algorithm it uses is very simple. It is looking for certain patterns in the cryptotext when it is comparing the cryptotext with a key string. Human language tends to use double letters. In the trivial example which I gave earlier, it had the word message, which has 2 S's in it. German, of course, works the same way. Das Wetter, zum Beispiel. Teletext control characters tend to be repeated. If you want to send something that is a series of numbers, and you've already been sending something that was a series of letters, the tendency would be to use the figure shift key twice to make sure that it actually shifted at the far end into figure shift. Additionally, you might well use 2 carriage returns and 2 line feeds so that the receiving machine didn't run off the end of the page, or that it didn't overprint previously printed information. Now, if you're comparing the cryptotext with the key stream, at the point where you have one of these double characters, and you're actually finding such a double character in the stream, in the data you're analysing, then a very simple algorithm applies that the key at the end position, exclusive OR with the message character at that position, along with the key in the next position and the message character in the next position, comes out to a nice simple number which is easy to detect, 0. This was the original message I was showing you. Once again, cryptotext is this middle character return SP, key and message. Where there's a double character in the message text, the original plain text, these 4 characters, when exclusive altogether, give you the value 0. And just as an experiment, I took this plain text message, so the original message, and did the process on a complete loop of all possible keys. Let's go to the next one. Okay. When I actually had the correct key position, then the double delta count is 4. Because there are 4 doubles in here, 2 letter shifts, 2 S's, 2 carriage returns, 2 line feeds. In all other positions, the double delta count never gets above 3. So it does seem that even in these modern times, the double delta method does work on messages of this sort. This is a simulator which I've written, which I won't go into in detail right now, as we're a little short of time. I will introduce one other concept, the index of coincidence, which is a mathematical process that you can carry out on a piece of plain text, a language text. And this is probably the only bit of math you'll have to do today, and I'm going to go through it real fast. But it's basically the sum of a function of all the letters divided by the number of letters in the message. And you end up with a number for various languages. The index of coincidence for German is different from the index of coincidence in English, which is different from the index of coincidence in Russian. You can detect if you're likely to have a plain text message compared with a crypto text message by the size of the index of coincidence. I've run my Colossus simulator through 10,000 versions of the plain text with 10,000 keys. This was the original message text. It has the highest double delta value, which is higher than all the other values for double delta, and also the highest index of coincidence. I should repeat that the index of coincidence was not used on the original Colossus. This is just something I've done for my own amusement almost. After 10,000 passes, when I sort the double deltas into order, I end up with 3 messages which could be the correct message, because they have the correct double delta, or the largest double delta. And then analysing further with the index of coincidence, I put the original text message that I had at the top of the list. And that's all I have to say on the subject. Thank you very much. Yes. Yes, the index of coincidence is different for each language. If there was enough message, yes, but the values do tend to be quite close to each other. But you'll find plenty of references to the index of coincidence in cryptography in all the well-known places. The Google. Keep this hand up, Fraga, or Nick? No? Okay.
Our next speaker is Professor Franz Pichler. He is a retired professor from the University of Linz, and he has written extensively, lectured, written, taught, thought extensively in the field of cryptology, early technology, and I think virtually every other extraordinary endeavor. So let me turn it over to Professor Pichler. You also have a book here to show people.
Thank you, Professor Perera. Yes, thank you. And thank you for the invitation to... okay, this is great, Tom. Thank you for inviting me to this meeting. I have prepared 4 different lectures, and I think I take a mix. And I think I will try to give the lecture in both languages, in English, which is very bad enough, and in German, which is also, as being an Austrian, very bad. Yeah? So maybe when we come, we might try the index of coincidence and to find out in which language I have given the lecture. Yes. Okay. The first lecture, I will skip most of them, but try then to explain what is the content. Ich werde die meisten Slides hier überspringen, aber ein wenig erklären, was es hier geht. First of all, of course, I was I have two traces of education. First, I got education as Fernmeldemonteur. Yes, ich habe einen Beruf erlernt des Fernmeldemonteurs in der Fernmeldemonteurschule in Graz. A long time ago. Das war 1950 bis 54. And later I studied mathematics, and in some extent I combined these fields, mathematics and communication engineering. Später studierte ich Mathematik und habe das kombiniert mit meinem Interesse für Radio und für die Fernmeldetechnik. And the field which combines this is the field of systems theory, where you use mathematical techniques to explore, engineering, communication engineering things. Systemtheorie ist ein Gebiet, das die beiden Gebiete, Mathematik und Engineering, zusammenfasst in einem Bild. Das ist sehr wichtig für Ingenieure. Und erfunden ist es eigentlich in Deutschland. Karl Küpfmüller war zuletzt in Darmstadt, ich habe ihn noch persönlich kennengelernt, hat das erste Buch Systemtheorie der elektrischen Nachrichten übertragen. So one of the inventors is German of system theory, Karl Küpfmüller, a great scientist and engineer. And he was in Darmstadt the last years, and I even met him personally. And it was already related with some work which can be used in Cryptology. Und es war schon ein Gebiet, mit dem man, dass Herr Küpfmüller hier mit mir auch diskutieren konnte. Ich war ein ganz junger Mann damals noch. Es war das Gebiet der Walsh-Funktionen, die damals von mir bearbeitet wurden, neben anderen. Well, I have then some experience in giving advice in system theory and in cryptography and cryptology, first to my students, but also to the Austrian army, and later on to companies, yes, in Austria and in Germany. And even I organized some meetings like Eurocrypt 85 in Linz, and so I am known, maybe until today, with the National Security Agency. I never had a chance to visit their museum, it would be very interesting. But once I got the invitation, yes, to apply for sabbatic leave. Ich war bei NSA sicher, bin bis heute registriert, wie vielleicht viele von Ihnen hier. Und ich habe sogar eine Einladung einmal bekommen. Und das sind die beiden Plakate, die an meinem Stand, das ist ganz in der Nähe beim Tom Enigma Center, habe ich die bekommen. Und ja, damals konnte ich eigentlich nicht so eine Einladung anstreben, aber heute bin ich zu alt dafür. Nicht? Aber jedenfalls ist es ganz nett. Die haben einen gewissen Humor, die NSA-Leute, weil hier sind alle möglichen Astronomen und Mathematiker der alten Zeit. On the left side you see all the important people of science and astronomy of past time. but also we see also John von Neumann. Yes, here. John von Neumann, one of the most famous mathematicians. John von Neumann war wirklich einer der ganz großen Mathematiker, ursprünglich in Göttingen, aber dann in Princeton. Und er war ganz wesentlich auch beteiligt an der Verbesserung der Rechner in Amerika, die ENIAC as the computer. So John von Neumann has many merits, and he was in Princeton, and he was very crucial to improve, say, the concept of architecture of a computer. And this is also here some picture where you see. Now, of course, this says that cryptology has something to do with computers, and finally, of course, we need the computer today to apply certain mathematical algorithms to find out about secrecy. Wir brauchen den Computer natürlich bis heute die besten. Cray 1 ist schon erwähnt worden, so, und die Supercomputer, um etwas herauszufinden, wie Kryptologen, Kryptografen Daten verstecken. Nicht? Also man muss das, ich kann das so jetzt deuten, Cryptologie sind zwei Gebiete. Einmal die Kryptographie, das ist das Entwerfen von Verschlüsselungsmaschinen, Verschlüsselungsalgorithmen. Und dann die Kryptanalysis, das ist das Überprüfen, die positive Seite der Kryptanalysis, das Überprüfen der Qualität von solchen Verschlüsselungsalgorithmen, oder, das ist die negative Seite, aber je nachdem, welchen Standpunkt man einnimmt, das Brechen eines Verschlüsselungsalgorithmus. So cryptology combines cryptography and cryptanalysis. Cryptography deals with the design, has a lot to do with the engineering also, and with mathematics of course also. And cryptanalysis is the field where you find out about the quality of your enciphering method, and also about this is the positive side of cryptanalysis, and the negative subjectively seen is that to break in. Now, of course, we need cryptography and we need cryptanalysis. Yes, so this is clear. And every company which designs cryptographic machinery has to have also a quality control, which is very difficult. Yes, of course, it should be. Now, let me look. This would be now, the lecture would continue here with my slides, which we skipped the most to explain the concept of secrecy and secret information transmission and so on. And then the outcome is that cryptography covers a lot to keep secrecy, to make it possible to transmit a message from Bob to Alice. Yes, these are always the people involved. Yes, in a secret way. This would be the subjects which we could deal, but we will just skip the part 1. We will just übergehen die Kryptographie auch in den essentiellen Dingen, Key-Management auch, das ist das Gebiet, wie erzeugt man Schlüssel, welche Qualität müssen die haben, wie müssen die verteilt werden. It is, and then String Cipher System, das ist eine spezielle Architektur eines Verschlüsselungssystems. So these are topics which should be covered in a course on crypto systems. We don't have the time and also not the interest, I'm sure. Yes, so I skip this very quickly. Let me see what we have here. this is, you see, these are definitions and so on. I have no nice pictures here. And then finally, defining of cryptography goals, progress. And well, here maybe we can stop a little bit. Wir brauchen für ein kryptografisches System Schlüssel, einen zum Zusperren, das ist der Senderschlüssel, und einen zum Aufsperren, das ist der Empfangsschlüssel. We need two kind of keys, basically. One will lock and one will unlock at the receiver. And so this is again the ciphering key and the deciphering key. Now there are two different methods in practice. There are crypto systems which use only one type of key, but enciphering and deciphering. And these are the most traditional used systems which are also in the history and so on. And the Enigma so is such a, can establish such a system. Und das sind die mit dem gleichen Key, das nennt man auch Secret Key System oder Symmetric Key System. Und dann die anderen, wo ein Schlüssel, und zwar der zum Schreiben, der Enciphering Key ist public, der ist öffentlich und sozusagen der ist publiziert. Jeder kann dann mit diesem Schlüssel an jemanden, Bob kann an Alice eine Message schicken und only Alice has the individual deciphering key. Das sind die Public Key Systems und das ist auch eine Erfindung erst von den 70er Jahren an. RSA, Reverse Chamber Element System, ist das populärste. Wir werden das nicht behandeln. Wir behandeln die Secret Key System und ganz eine spezielle Art der Stromchiffrierung. Das ist, was wir vorher schon gesehen haben bei dem Lorenz Schlüsselzusatz, the Lorenz Cipher machine we saw in the lecture before. It is they use a pseudo-random generator, and then it is a different application. Now, this would be historical, we will transfer, and I go now to certain books. This is a little bit more interesting, maybe to see cover of books. And these two books I have double, and they are for sale. If you are interested, each costs 10 euros. Thank you, Tom, for giving me the chance to offer. Now there are other books, and I show two of the most important books. If someone of you is really interested in the mathematical background of cryptology, not only in the engineering, technical, then these are, of course, two very important books. On the left, this is a kind of Bible. Yes, written by Belgian scientists, the Handbook of Cryptography, of Applied Cryptography. It is, to my knowledge, this is you find many things. This is amazing. And the right thing is from Bruce Schneier, Applied Cryptography. Das gibt es auch in Deutsch, angewandte Kryptographie. I think in the foreword, Bruce Schneier writes. He was thrown out by a company and now he had time, being without work, to write a book. Ja? Bruce Schneier hat das in der Zeit seiner Arbeitslose, weil er von einer Firma Gott sei Dank für uns rausgeschmissen wurde, hat ein Buch geschrieben. Das ist sehr gut. Schneier ist wird heute sehr viel verwendet. Und dann gibt es andere vom F.L. Bauer, ein berühmter Professor aus München, F.L. Bauer. I know him personally, and he's a great man in the late 80s, yes, so I hope he's still alive. I would have heard maybe, yes, so Decrypted Secrets, entzifferte Geheimnisse auf Deutsch, and an older book by Alan Kahnheim on cryptography, which has a lot of cryptanalysis in it. Yes? You see, people are always looking where stands the cryptanalysis? Conheim is a book. And then we have David Kahn, a great historian. I never met him personally, but he has contact with friends of mine, or Winterbottom, the Ultra Secret, and others. And I have, being Austrian, also mentioned that in Austria we had in the time of First World War a quite high level in cryptography. Als Österreicher möchte ich nur erwähnen, dass auch gerade in der Zeit des Ersten Weltkrieges und nachher eine große Gruppe und sehr wichtige Leute waren. Einer war der Andreas Fiedel und ein anderer Dürtel, ist bekannt auch durch Bücher, auch die Enigma-Maschinen der ersten Zeit. Mein Freund, leider schon verstorben, Otto Horak, hat mir eine Biografie über Oberst Andreas Fiedel geschrieben und ich habe von seiner Witwe Restexemplare bekommen und für 15 Euro kann man das kaufen. Das Geld geht an die Witwe. Ja? Das ist also nur, man findet das kaum mehr, glaube ich, sonst nicht über den Buchhandel, aber wer ist interessiert, es sind, glaube ich, 5 Exemplare hier. Und von Fiedel gibt es Systeme des Chiffrierens. Jeder, der sich mit historischen Chiffrieren, der sollte dieses Buch haben. Und ich habe auch ein zweites Exemplar zu verkaufen. Es ist leider nicht ganz billig. Das ist mit solchen Büchern von 1927 für spezielle Art der Fall. Aber wenn Sie sich interessieren, können Sie gerne anschauen. There's a second original book from Andreas Fiedel here to sell. Yes. Okay, Tom, we go now to, I think, how many minutes do I have? 5, 10? 10, let's go to this stream side. Yes, thank you. How does this function? The mixing of German and English, is it okay? I'm not keeping it always in the right order. So it is not, ich glaube, Sie bringt das ein bisschen durcheinander, das ist nicht ausgedacht. Okay. Ja, es ist String Ciphering, das ist wohl die wichtigste Methode, wenn es auch heute für Militär geht, für Diplomatie und auch für kleinere Anwendungen von geschlossenen Gruppen. String ciphering, I think, is still one of the most important methods. It also is simple. We had it also before. We had a string cipher here with the Lawrence, if I'm right, and it is used in military and in diplomatic, applications, but also if there are small user groups. So if I would have, a not too big company, which has, external, offices, I would not take the recommended general cryptological methods like data encryption standard or advanced encryption standard or others. I would go to a special company and say, please design for me a special string cipher. Which is at least my personal thing, because you will see it is simple to implement today. Yes? And the cruise is the state of the art of memories. Yes? We can store a lot of data on memories today, and if you don't send too many pictures and movies and so on, then you have enough memories. So es ist, wenn man so kleine Usergruppen ist, das Stromschwierung sehr wichtig. Und ich möchte Ihnen nur die Idee zeigen und dann auch etwas, wo ich selber mitgearbeitet habe, erklären, das zu einem Resultat führt, wo ich sogar ein Gerät hier auch mit habe. Mein Stand ist E054, so I'm close to Tom Perera's Enigma Center. You can find me, usually my wife Ilse is there, And we have even, we will see the machine, which at least a German museum has shown some interest already, to buy maybe this machine. It would be nice. It's just a normal telephone. It looks like a normal telephone. Ja, schauen wir uns einmal ein paar Bilder an und ich versuche die zu erklären. Wir können da nicht alles genau erklären, aber damit Sie die Idee bekommen. We just look for a few slides and maybe we get the idea to find out what it's all about. Was ist wichtig bei einer Stromchiffrierung? Wir brauchen entweder einen echten Zufallsstrom von Daten. Gewöhnlich kann man hier an Bitfolgen denken, 0 und Folgen von 0, 1, sehr lang, die echt zufällig sind. Wir nennen das die Schlüsselfolge. So, essential thing is you need a very long, say, true random sequence of bits, and we call it the key sequence, and this is necessary. Now, the key sequence is mixed with the data sequence just by what has been mentioned before, by addition modulo 2. So 1 and 1 is 0, 0 and 0 is 0, 1 and 0 is 1, and 0 and 1 is 1. This is addition modulo 2, it is called so, or XOR. And this is of course very easy to implement, and the famous one-time bad system works in that. It is always told that the red telephone once between Washington and Moscow, they used such a one-time bad. Es wird immer wieder berichtet, dass das berühmte rote Telefon zwischen Moskau und Washington mit so einem Stromchiffriersystem, wo eine Zufallsfolge verwendet wurde, eingesetzt wurde. Nun, was ist das Problem hier? Das Problem ist, dass an der Empfangsseite die gleiche Zufallsfolge existieren muss, und das Problem ist auch, dass das bit-synchron ablaufen muss. The problem is that we have to have on the receiving station the same true random key sequence, and also that it is synchronized with the key sequence by which the data on the sending station are mixed. Now, to overcome these problems, of course, this can be, if you have slow data, then this can be done, and you can store, say, in a random sequences on certain memories on both sides, and select by a certain protocol from one to one you select. And according to Claude Shannon's theoretical investigation, you should use a pure random sequence only once. So if you need this, you need a lot of such sequences. Der berühmte Mathematiker Claude Shannon hat aber mal theoretisch bewiesen, man darf so eine Folge, so eine Schlüsselfolge nur einmal verwenden. Ja, das ist ein bisschen theoretisch, das ist nicht so ernst zu nehmen vielleicht. Aber wir müssen die Lösung, die angestrebt wird, wenn man nicht, das ist ein Schlagwort, die Quantenmechanik heranzieht für zukünftige Systeme. Die Lösung ist, dass man keine echte Zufallsfolge nimmt, sondern eine Pseudo-Zufallsfolge. Man erzeugt mit einem Generator eine sehr gute Folge, die nahe einer Zufallsfolge ist. Now the solution is that you have a key generator on both sides, which is able to generate a pseudo-random noise of good quality. Of course, this is a question. What is a good quality of a pseudo-random noise? and this is not so easy to answer. One of the best, books which deal with this is from Donald Knuth. He's really one of the still living famous computer scientists in the States, and in his books you find really good indication of it. At least I found this. And das ist einmal das eine. Man braucht also einen Erzeuger, einen Generator, das muss eine Ingenieur- und Mathematikarbeit sein. Das andere ist, die Synchronisierung muss gemacht werden. Das ist auch eine gewisse Schwierigkeit. The synchronizing both, generators is also a question of, not so easy. Okay. So the architecture would be of such a system. We have a pseudo-random generator and a mixing operation. Das ist die Architektur von einem solchen System. Ein Pseudo-Zufallsgenerator, der startet mit einem bestimmten Schlüssel, erzeugt eine Zufallsfolge, Pseudo-Zufallsfolge Y, und das Signal, der Klartext, wird gemixt mit XOR für einen Ciphertext. Und ich gehe jetzt weiter. Das ist Ihnen kein Geheimnis, aber das ist die Praxis, wo man sagt, ja, das sollte man machen. Wie baut man so einen Zufallsgenerator, Pseudo-Zufallsgenerator? Also eine Linie, die man verfolgen kann, ist, man baut L, in dem Fall M Pseudo-Zufallsgenerator, so gut man sie kann, und verwendet sie parallel und kombiniert die Output-Folge x1 bis xm mit einem Combiner. Das ist eine Architektur, die vielfach angewendet wird. Ich habe das selber im praktischen Beispiel gesehen. Und damit kann man eine Verstärkung. So this is an architecture of a random generator which can be used. You have n pseudo-random generators of certain high quality, and you combine them by a box C such that the resulting pseudo-random sequence Y is much stronger as the other one, the X1 and XN. And for the construction of the individual pseudo-random generator, well, the advice is to use, concepts which are mathematically sound, which you can follow. And there are shift registers, which you know from engineering are at least very good means for it. Schieberegister sind wichtige Bausteine, um Pseudo-Zufallsgeneratoren zu bauen. Und das ist die Theorie des Schieberegister, die von Golomb in den 50er, 60er Jahren startete. The theory of shift register started very early in the 50s, 60s. Solomon Golomb, I come to the end. And there are different generators in the open literature which are known here. Now, I have to mention a little story. When I made my first visit at the University of Maryland in 1970, I was also a beginner in cryptology. And I got some advice. Well, in that time, 1970, believe me, for me, maybe only 5 publications were known dealing with cryptology in the open literature. This was the situation at that time, not a long time ago. Yes? And Cipher was known. I don't know if I pronounced it right. And I heard that he is near Washington, maybe in Baltimore, and I called him up. Yes? And I say if I could meet him and discuss some of cryptology. Yes? Maybe it was with NSA, I don't know, I didn't know. And he said, well, you come from Austria and you have such a high tradition in cryptology, so I can't tell you anything new. So So, ich habe Käfer angerufen, damals 1970er, nun müssen auf Maryland, aber er war zu keinem Gespräch, er hatte keine Zeit für mich oder wie, ich weiß das nicht mehr so genau. Er sagte, ihr Österreicher habt sowieso eine große Tradition in Kryptologie und muss nichts erklären. But here, of course, already some men which are well known, like Messi and Rüppel, later with Crypto AG. Wolfram is very known in the States, and here also. So there are a number of, and we developed, and I come now to an end. We developed at Linz University at that time our own method, yes, of what we call clock-controlled shift registers. It was not new, but because some other work was kept secret and we didn't know about this. I think in Norway they had also some studies of that kind. And but we were in that time we were quite good to investigate this. And I had a very good student, Dieter Goldmann. He is now a professor of cryptology in Hamburg. Yes, Dieter Goldmann. And we investigated these shift registers. I don't explain it, but it is simple enough. You have you clock a shift register in its movement. You stop it and let it run, like the wheels in an Enigma machine can be stopped and again run, yes, and so on. And the results were quite good. We had a mathematical theory, the Goldman cascades, and we even built then a machine using these Goldman cascades. And it got really a practical application by the water coder 2400. I worked together with Hubert Kukler in that time, the chief of water communication Mainhausen near Frankfurt, a great engineer. Unfortunately, it's not anymore alive. I never met such a fascinating person. And this was the result. It was a normal telephone which had in the base, it was much more heavy, yes, and in the base a crypto device, and this is the crypto, and it used 15 such cyclic shift registers in a certain combination, and I have it also. You can look at this on my stand, and I want. You see, I go. The best would be I give it to a museum, yes, because it is only one piece maybe available. It was an export. It was exported. As you can see, it is not military. It went to outside country. I don't tell you in what country. I know it, yes, but it may be better not to mention this. But it was used in a closed group of users, yes. Whenever you push the start button, you had voice encryption. 2400 refers to 2.4 kilobit compression of voice. Yes. Thank you very much.
Thank you very much, Franz. And Franz's table is E054. And you can see that machine right on his table. It's amazing.
Also the NSA posters.
And the NSA posters. So definitely go and visit him fairly close to the Enigma tables. One more thing, I ask you if you have any suggestions for next year. We will try and have another forum next year. My card will be up by Klaus's Enigma, and you can send me an email with any suggestions, people that you would like to have speak or not speak, and whatever might be interesting. So thank you for coming, and let's go on with Klaus then.